Welcome to some more Corpio revision. Today we're going to take a look at some last minute exam revision. So it's the Corpio 2 exam tomorrow. So first off, I just want to say good luck to everyone who's seen it tomorrow. I'm sure you'll all do great. I'm sure you've all done enough revision. But just in case you need some last minute revision, let's take a look at some questions. So pick some questions from Corpio 1 book and the Corpio 2 book. So there's a mix of things. Everything that's in Corpio 1 textbook you do need to know anyway. So it's worth practicing questions from that as well. Such as vectors and the roots of polynomials, for example. So let's take a look at some questions here. We've got a mix of them, so let's start off. So the first question is taking a look at series expansions from Corpio 2. So get my pen. So we've got this series expansion here for sin x and cos x, and we want to show that 3 sin x minus 4x cos x plus x is equal to 3 over 2 x cubed minus 17 over 120x to the 5, plus so on and so on. So 5 marks for this. So how do we begin with something like this? Well, for a question like this where you have to use the series expansions, what I'd do is I'd write them down individually. So these are given in your formula book as well, so you don't need to worry about memorising these. So sin x, so we write this down first, so sin x, that's going to be equal to x minus x cubed over 3 factorial plus x to the 5 over 5 factorial plus so on and so on. Now notice I only need to stop at x, I can stop at x to the 5 because that's the highest power here. After that everything's kind of just been negated, so we don't need that. So that goes on and on. We'll simplify it in a minute what that would be. Cos x, that will be 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial. And again, I can stop here because I'd have x to the 6, and that's too far. We're stopping at x to the 5 anyway, so we don't need to worry about that now. We can't really simplify this, but what I'm going to do is I'm going to write this, instead of it being like 3 factorial, for example, I'm just going to evaluate 3 factorial. So this will be x minus 3 factorial, so that's 3 times 2 times 1, so that's 6. So this is minus 1 over 6 x to the 3, x cubed. Now you can write it as x cubed over 6, but I'm going to keep it like this just so I can see when I have to do the subtraction after. It just makes it a little bit easier to see. And 5 factorial, so that's 5 times 4 times 3 times 2 times 1, so that's 120. So this is plus 1 over 120 x to the 5. Okay, so that's that bit. Obviously we have the rest of it. We just do the same here, so this is 1 minus x squared, or 1 over, sorry, so we're just going to that, x squared, 1 over 2 times 1, so that's 2, so it's half x squared, plus 1 over, again, 4 factorial, so that's 4 times 3 times 2 times 1, so that's 24, so it's 1 over 24x to the 4 there. Okay, and we'd subtract off the next term there. So far, that's good. All we need to do now is apply this part here. So what we're going to do is we're going to times our expansion here by 3, because it's 3 sin x, and then we're going to times the expansion for cos x by 4x, because that's what we're required to do in the question. And then in the very end, we need to add an x like we're doing here. Okay, so therefore 3 sin x minus 4x cos x plus x, okay, so just make sure we get everything down. Well, that's going to be equal to 3 lots of x minus 1 over 6 x cubed plus 1 over 120 x to the 5 there. Okay, so that's okay so far. And then we need to do the same with the cos x, but minus 4x in front of it. So we times it by minus 4x here. Write everything down again. So 1 minus half x squared plus 1 over 24 x to the 4. And then we need our plus x at the very end. Okay, so hopefully this is clear so far. So all we've done so far is writing the expansions individually, and then we're timesing it by the 3 here, and then the minus 4x here, like we're doing here and here. Okay, So all we're going to do now is just simplify everything and collect like terms. So 3 times x, so just do it over here, that'll be 3x. 3 times minus 1 over 6, so that'll be minus a half. Minus a half x cubed. And then 3 times 1 over 120, so that'll be 3 over 120, so we can simplify that as 1 over 40, so plus 1 over 40 x to the 5. Carry on again now. So minus 4x times 1, so that's minus 4x. Minus 4x times minus 1 over 2x squared, so that'll be 2x cubed. So just be very careful with your signs here. So that's going to be positive, 2x cubed. And then finally my last one here, this will be minus 4x times 1 over 24x to the 4. So that's going to give me minus 1 over 6, and then it's going to be x to the 5. And then don't forget you plus x at the very end. Okay, and then we're nearly there. So let's have a look if we can cancel anything. So I've got 3x plus x minus 4x. So straight away, they're going to cancel. What else do we have? We have a 2x cubed here minus a half x cubed here. So what that's going to give me is 1.5 or 1.5. So that'll be 3 over 2 x cubed. And so we've dealt with that. If we just cross them off just so we can see what we're up to. So we've got 1 over 40 x to the 5 minus 1 over 6 x to the 5. So you simplify that, and what you'll get is minus 17 over 120 x to the 5 there. And that's just as we required it. So we add on the extra bit there, because that series would carry on. But there we have it. So we've shown that 3 sin x minus 4x cos x plus x is equal to this expression down here in the bottom right corner. Okay, so that's part A done. If we just clear all this now just so we can do part B, it's a nice easy one marker. So we erase all the ink, carry on writing. So 8B. So we're going to find the limit as x tends to 0. Okay, but notice it's our original expression in part A, but it's divided by x cubed. So even if you couldn't do part A, you can actually have a go at this, because they give you what it should equal. So if you think about it, they've done 3 over 2 x cubed minus 17 over 120 x to the 5 divided by x cubed. Now if you think about simplifying this, this would be 3 over 2 minus 17 over 120 x squared plus so on and so on, right? That would carry on. So what I've kind of done here is just carried on with the expansion, but now you've got to think about what would happen with each term past the x squared, for example. So as x tends to 0, so as x tends to 0, so if you put like a really, really small number in here, this is also going to tend to 0 as well. Okay, so in a way, everything past here is just going to be negated. We're not going to need it. So all I'm actually going to get left with for my limit, so as x tends to 0, the limit will be 3 over 2. And that's simply it. So the limit will just be 3 over 2. So all they've done, divided 3 by x cubed, and because we get left with this 3 over 2 here, there's no x's with it. We're just going to get that as our limit there. Okay, so that's the first question done. Let's take a look at the next one. So this is an integration question. So this is methods in calculus. So exercise 3D from Core Pure 2, question 7. So let's have a look at tackling this. So we've got to find the integral of 1 over, so 1 over the square root of 4 minus x squared between root 3 and root 2 dx. Now it actually asks us to show that this is equal to pi over 12. So this shouldn't be too bad. This is something that comes with practice, but something should be jumping out right now at us for this, and that's the fact that this here, this 4 minus x squared, is in the correct form already. So this is actually an integral here of the form 1 over the square root of a squared minus x squared. Okay, Now an integral of this form, if you look in your formula book, you'll know exactly what this is. And this is just arc sine of x over a. Okay? So, using that information now, let's show that this integral here is equal to pi over 12. So if we carry on with this, this is just going to be now arc sine, so arc sine, sine inverse, your x over a, so that's just going to be x for us, because imagine you take the square root of x squared, you just get x, take the square root of this a here, and this has to be 2, okay? So that's how we get this term here, and we are doing this between the limits here, root 3 and root 2, okay? So, all you've got to do now is sub your limit in here, root 3, where your x is, minus this again, but with the limit of root 2. So if we do that, that'll be arc sine root 3 over 2 minus arc sine root 2 over 2. Okay, so just be careful we don't get this the wrong way around. So, my cat's being very loud. So arc sine root 3 over 2. Well, you can just put this in on your calculator, right? This would just give you pi over 3. Or if you're not off the top of your head, that's pi over 3. Arc sine root 2 over 2. So that'll give you minus pi over 4. Now, all we've got to do is just simplify this. So this would be the same as 4 pi upon 12 minus 3 pi over 12. And if you simplify this, that's just going to give me pi over 12, which is exactly as they've asked for. And it gets us all 4 marks there. So the key for that question here is spotting that this integral this integral here straight away is in the correct form. You don't even need to do any modifications to it, which is usually the case with these questions. But sometimes, if it's early on in the exam, you might get lucky and get one. You don't need to do anything like that. Okay, so pi over 12, nice and easy. So the next one, we're taking a look at 3x3 matrices. This is from the Corpio 1 textbook. So what we're actually asked to do is show that this matrix here is singular. Now, you need to know how to do this by hand, because for questions like this, for example, you can't do this on your graphical calculator. If every term in the matrix is a number, that's not a problem. But if you have any algebra, then it becomes an issue. So, we need to have a go at tackling this determinant. Now remember, if I write this matrix out, 0a minus b minus a, 0 c, b minus c, and 0. Now, to find the determinant of a 3x3 matrix, you can expand along any row or column. But what I do is I always expand along the top row. So I'm expanding along this top row here. And what I mean by that is that I start with this term. So when I start with this term, what I'll do is I'll just change my pen colours to make it clear. I'm going to erase this row and then this column. So all I actually get left with is this 2x2 determinant down here. Now because it's 0, it would be 0 lots of 0, c, minus c, and 0. Now I didn't need to write that out because 0 times anything will just be 0. But just so we can see what it is, that's what it would be. Do the same now. Again, I'm going to change my pen colour, change to blue this time. I'm going along this row again, and I'm going down this column this time now. So I get left with minus a, c, b, and 0 there. Now normally it goes positive, minus, positive. So because this is just a, that's going to be minus a there. So that's going to be minus a, c, b, and 0 there. Okay, that's looking good so far. And then if I just change my pen colour one more time, what colour can we be? Let's be red. So again, we're going along the same row again, but this time we're deleting this column. So I get left with this 2x2 matrix in the bottom left corner. So it's going to be positive b, minus a, 0, b, and then minus c. Okay. And all I need to do now is work out each individual 2x2 determinant. So if we go back to white to finish this, so that's going to be 0. minus a times the determinant of this, so minus a times 0, so that's 0. And then it's going to be minus b times c, so that's minus bc. So minus a times minus bc, so I'm going to get positive abc. Okay, so just be very careful that has to be positive abc. I've got plus b, lots of this 2 by 2 determinant, minus a times minus c, that's ac, minus b times 0, so that's just minus 0. So ac times, have I done something wrong here? Yeah, that should be minus, sorry. So yeah, so this is plus, minus, plus, what's wrong here? Have I copied something down wrong? Sorry, yeah, so because this is minus here in the top right, this should be minus. So we're going to say that's not working, so that's minus b there. So minus a times minus c is ac, times minus b, we get minus a, b, c. Okay, so I'm going to say something's not working there, because if it's singular, remember, the determinant should be 0, which that was going to give me, that definitely wasn't going to give me 0, so I knew that something had gone wrong there. And that's a good check for yourself, so me making that mistake there hopefully will help you guys. So ABC minus ABC, they just cancel and we get 0. So therefore the matrix is singular as determinant is equal to 0. Okay. So that's that question done there. I'm going to quickly pause it and go sort my cat out because it's being crazy. So moving on now, we've got a question here dealing with 3D vectors. So this is a notoriously tricky topic for a lot of people on the A-level for maths. But this question, I've just took a little bit shorter from the actual full question. It's quite a long one for the full thing. So let's just have a look at the two parts that we've picked out here. So we've got the equations for two different planes, pi 1 and pi 2, and the first part just asks us to show that the point A2 minus 2, 3 lies in the plane pi 2. So to show that a point lies in a plane, what we need to do is we need to use the dot product of that point and then my vector for pi 2, and what we should get is that it's equal to the r dot n equals d, so it should be equal to d here, which is 1. So let's just write that out. So what I'm saying is 2 minus 2, 3 dotted with 1, 5, 3. This should give us 1. So 2 times 1, so that's 2. Minus 2 times 5, so that's minus 10. 3 times 3 is plus 9. So 9 plus 2 is 11, minus 10, that's equal to 1. Perfect. Okay? So because that equals 1, therefore we can say that 2 minus 2, 3 lies on pi 2. Okay? So that's all we've got to say for that one. Just showing that the dot product there gives us the d, which is 1. For part B, we have to show that pi 1 is perpendicular to pi 2. Well, again, showing that two planes are perpendicular like this, again, it involves the dot product. And to show this, what I need to do is do the dot product for the two different vectors. Now, if they are perpendicular, remember, the dot product should be equal to 0. So if it's not equal to 0, then they're not perpendicular. But if they are equal to 0, then it means the two planes are perpendicular. So if we do this, that's going to be 2 minus 1, 1, dotted with 1, 5, 3. And again, working this out, this is 2 times 1, which is 2, minus 1 times 5, minus 5, and then 1 times 3 is 3. 2 plus 3 is 5, so we've got 5 minus 5, which is equal to 0. Boom, perfect. We've got everything we need there. So what we'd say then is that pi 1 is perpendicular to pi 2 as the dot product or the scalar product is 0. Okay, so we kind of got through that quite quick, but hopefully it's kind of clear that that question relies a lot on the dot product. So make sure you're confident with the dot product, and then just be confident as well in the fact that two planes are perpendicular. When you do the dot products of them, the result should be equal to 0, like we got here. Okay, and there we have it. So that's that question done. Let's take a look at the next one. So this is a nice easy one. Thought I'd throw it into the middle just as a bit of a respite. We've got question 4a. So we're given this complex number here. So z is equal to 4 cos 2 pi over 3 plus I sine 2 pi over 3. And we've got to write it in this form x plus iy. And x and y are just real numbers. So how do we do this? So let's just write it down. Plus I sine 2 pi over 3. Now, cos 2 pi over 3, what's this? If you put it on your calculator, what would you get? Well, what you actually get is that cos of 2 pi over 3 is actually just minus a half. Okay, so that's minus a half. What about sine 2 pi over 3? If you put that on your calculator, what you should hopefully get is that this is root 3 over 2. So this is I root 3 over 2. So we've got these two different expressions now in the bracket. We've got our minus a half and our root 3 over 2i. So all we need to do now is just times it by the constant on the outside, the 4. So 4 times minus a half, that's minus 2. And then 4 times root 3 over 2. So 4 will divide by the 2. So I'm going to get 2 root 3 I, or I 2 root 3. So let's write that down. That'll be plus. How we would normally write is 2i root 3 like that. Okay, so just a nice easy one there for 2 marks there. And then part B just asks you to show this complex number z on an diagonal diagram. So nice and easy. Make sure yours is neater than mine. I can't even draw a straight line, so I'm definitely not good at that. Remember which way your axes go. So this here, your x-axis would be real, and this y-axis is your imaginary there. Now, the complex number we've got is minus 2 plus 2i root 3. So remember, how do we decide which way we go? Well, the minus 2 here is the real component. So we go minus 2, so that's 2 to the left. So we're going to go 1, 2. We'd say it's about there. And we've got 2 root 3 on the imaginary axis. So 2 root 3, we can say it's roughly about here. Okay, so that's my z there, which is equal to minus 2 plus 2i root 3. Okay, so we'll say it's that point there. That'll be minus 2. And we'll say that's 2i, or 2 root 3 there on the imaginary. And there we have it. So that was just a nice quick question there. Hopefully confident with complex numbers, very important for the full corpuscular. So let's have a look at the next one. Again, this question, looking at series expansions. Now this time we're dealing with the exponential function. So we've got to show that for small values of x, e to the 2x minus e to the minus x is approximately 3x plus 3 over 2 x squared. 4 marks for this. So just like we said for the last series question that we did, the very first one, write out your expansions individually. So my two expansions are going to be e to the 2x. So we write that one out first. So that's going to be 1. Again, use your formula books. It's 1 plus 2x plus 2x squared over 2 factorial plus 2x cubed over 3 factorial, so on and so on. Okay, so we don't need to carry on, but we'll simplify that in a second. And then my other one is the e to the minus x. So e to the minus x, well, that'll be 1 minus x plus minus x squared over 2 factorial plus minus x cubed over 3 factorial plus so on and so on. Okay, and we want to know what this is equal to. Again, we're going to simplify both of these. Well, this will just give me 1 plus 2x straight away. 2x squared, so that'll be 4x squared divided by 2. That's just going to give me plus 2x squared. And then 2x cubed, so that'll be 8x cubed divided by 3 times 2, so 6. So that's going to give me plus 4x cubed over 3 there. Okay, and that would carry on. Let's do the same with this e to the minus x, and then we can apply it doing the subtraction there. That's going to be straight away 1 minus x. So because this is minus x but it's squared, it'll be plus x squared. So that's plus x squared over 2. But my next one will be the negative one. So minus x cubed, that will be minus. So that's going to be minus x cubed over 6 there. Okay. So we've got our two expansions individually. All we need to do now is do e to the 2x minus e to the minus x. So therefore, e to the 2x minus e to the minus x is going to be equal to, or we can say it's approximately, so that will be 1 plus 2x plus 2x squared plus 4x cubed over 3. What I'm going to do is I'm going to write this in one bracket just so we can see it. So that's my e to the 2x. We're going to minus off these terms now. So 1 minus x plus x squared over 2 and like that. Okay. So all we've got to do now is just simplify. So 1 minus 1. So they cancel straight away. I've got 2x minus minus x, so that has to be 3x. So we cross them off just so we can show you that we've dealt with them as well. I've got 2x squared minus x squared over 2. So what will that give me? Well, that'll just give me 3 over 2, because it's 2 minus a half here. So it's going to be 3 over 2. It's 3 over 2 x squared. Now, I went one over here with the 4x cubed. But we don't actually need it. Seeing as it's what it's done is it's got rid of all the values higher than x squared. So they've just said for all small values of x. So therefore, this is what we've got as required. Omitting x cubed and further terms. Okay, so these questions are very similar when it's something like this, where you've got to show that some kind of expression is approximately something else. So always write down your expansions individually and then apply your operation, whether it be subtraction or addition, whichever it is. Okay, so 4 marks for that. Hopefully nice and easy. Let's take a look at the next question. So this question here is a proof by induction question, but it's one of these questions where a student's done some work in, but they've made a mistake and we've just got to spot the mistake basically here. Now, this is a very generous question because for 2 marks for just identifying the error is quite nice, because let's just think about how a proof by induction actually works. So what they've done is they've said assume that the statement is true for n equals k, and then they've changed the n's here to k's, which is fine. And then they've said when n is equal to k plus 1, which is fine again, but what they've actually done, and hopefully it's clear to you guys, they've missed the very first step of a proof by induction, which is the base case or the basis step. So the student has missed or forgot the basis step. So that's usually when we say, for example, n equals 1, right? Now, I'm going to kind of rule n equals 1. So I'm going to actually take an example now. So I'm going to use that for my part B as well. So let's have a look at part B here. So normally we say when n equals 1. So let's consider what happens when we do that. Well, the left-hand side, well, that's just going to be the sum from 1 to n here. Okay, so from 1 to it's from 1 to 1, which is just going to be 1. So therefore my left hand side is just going to be 1. My right hand side is going to be a half of 1 squared plus 1 plus 1. So the right hand side is a half of 1 plus 1 plus 1. Now 1 plus 1 plus 1 is 3, and then we times that by half, so it's going to give me 3 over 2. But clearly 1, so we do this up here, 1 is not equal to 3 over 2. So there's a contradiction, right? But this gives us our counterexample to show that the original statement is not true. So there we have it. So that's that question kind of rolled up into, I've kind of basically done it in one step. Now 2 marks for this, like I said, is very generous. I think that'd normally be 1, but that's how Edexcel has done it in the textbook. But for these kind of questions, guys, if you're really struggling to actually see what the error is, just do the question yourself and then compare your answer to the student's. And then hopefully you've not made the same error as the student, because if you have, then you're not going to get anywhere. But if you've done it all correct, you should see eventually from your line of working where the student's gone wrong. Okay, so that might be something to help you with these kind of questions. But let's have a look at the next one. This is from exercise 7F from Core Pure 1. So this is dealing with linear transformations. Now, we've got this 3x3 matrix here, M, and we're told that the point ABC maps to the point 3, 2, minus 1 under M. Now, for this question here, this is where a graphical calculator is really, really important. If we want to find out what this original point is, we're going to need the inverse of M. Now, with it being a 3x3 matrix, to work out that inverse, it's going to take us a bit of time. But with a graphical calculator, and Edexcel expect you to do it, for 4 marks, they're not expecting you to sit down and work that out individually. So just put it on your calculator. If you put it on your calculator, you'll get 2, 3 over 2, minus 1, 0, 2, oh, sorry, 2, 3 over 2, minus 1, so that should be minus 1, I'm copying in the wrong matrix, so minus 1, and then 1, and then finally minus 1, minus 3 over 2, and then 1. Okay, so I can't even do it when I do it from the calculator, so I'm doomed, but you guys aren't. So if I carry on with this, using this M inverse now, if I do M inverse, so if I use M inverse, then times it by the point that we got, which is 3, 2, minus 1, this will give us then that A, B, and C value. Okay, so if I write that out now, so this is 2, 2, minus 1, okay, so I didn't get it wrong this time. Times it by 3, 2, and minus 1. Again, just do this on your calculator. They don't expect you to do this by hand. And then if you put this onto your calculator, what you're going to get here is 10, minus 6, and then minus 7. Okay, so therefore, the exact values of A, B, and C. A is 10, B is minus 6, and then C is minus 7. So, quite a nice question really for 4 marks if you've got a graphical calculator. Without a graphical calculator, that question becomes a lot longer, and it's easy to make the mistake without the calculator, but it's nothing too tricky. Just be aware of the fact that if you've got an inverse, you can times it by the point then to get your original point here. So this is your A, B, C there. Okay, so hopefully that's not too bad. Again, it was quite a quick one, but obviously I'm not showing you exactly on what I'm putting on my calculator screen, but that should hopefully be quite an easy standard skill for your core pure anyway. So let's move on to the very final question here. Just a nice easy 2 marker just to finish off. I've actually got this wrong, so this, I'm going to quickly rewrite this. I knew I'd get it wrong for one of them. So it's actually exercise 1C, question 6 from core pure 2. Okay, so I knew I'd eventually get one wrong. I always do, but it shouldn't take away from the revision. So for this question here, question 6, we're given a complex number. So W, 2 lots of cos pi over 6 I sine pi over 6. Now we're asked to find the exact value of W4. So how do we do this? Well, what we've got to do is we've got to apply Demoivre's theorem. Now, the reason we know we're using Demoivre's theorem is because it's a complex number with high power. So with it being W to the 4, I can write this as W to the 4. This is going to be equal to, so when you apply Demoivre's theorem, remember, if it's W to the n, then the number here on the outside, this would be 2 to the n, and then we times our angles here, cos pi over 6, and then I sine pi over 6, we times them by n. So it's going to be cos 4 times pi over 6, that'll be 4 pi. So what I'll do is write this down, so that's 2 to the 4, cos 4 pi over 6, plus I sine 4 pi over 6 again. We can simplify this in a second. So 2 to the power of 4, hopefully nice and easy, that'll be 16. This cos 4 pi over 6, we can simplify that as 2 pi over 3. So that's 2 pi over 3 plus I sine 2 pi over 3 as well. Well, now, this is very similar to the first complex number question we did in this video, where we want to write this now in the form a plus ib using this information here. So again, just plug this in on your calculator. There's going to be 16 lots, and in fact I think it's actually the exact same values. So cos 2 pi over 3, that'll be minus a half. Okay, same again here, sine 2 pi over 3, that's going to be root 3 over 2, so it's plus I root 3 over 2. And then we times it through by 16. Okay, so that's going to be equal to 16 times minus a half. So it's going to be minus 8. Plus 16 divided by 2, so that's going to be 8 lots here. So it's going to be AI root 3. Okay, so 2 marks for that. But it's quite a nice, easy question. Okay, so that's it for this video. It's quite a brief one. Hopefully I've not run over too long. Like I said, good luck for tomorrow. If you're still actually watching this, I'm very impressed that you've got to the end. But take your time, don't rush anything, and hopefully you all do amazing, smash it, and get whatever you need to get into uni or any job. But yeah, good luck, guys.